Today we are going to talk about a way to show a structure of how the electrons are located around the nucleus of the atom. We call this orbital notation. When we write orbital notation, we obey a principle called the Aufbau Principle. The Aufbau Principle says that electrons in the atom enter orbitals of lower energy first. For instance, if you have the nucleus in the center, then in the first energy level out from the atom, you are going to have that particular energy level full first before you go on to the second energy level, and then the second energy level will fill up before you go on to the third, etc., etc. So it simply says that the electrons enter the atom in the energy levels closest to the nucleus first and fill those up from the inside out. Now, if that's true, it would seem to indicate that they would enter the atom, enter that electron cloud in this order. And remember from the notes we took last, the first energy level has just an S sublevel, so that would fill up. The second energy level has an S and a P, that would fill up. Before we went to the third energy level, which has 3S, 3P, and 3D, on to the fourth energy level, 4S, 4P, 4D, and 4F energy levels, and finally, we just keep continuing on out from there. But what we find is that this isn't what happens. We do find it first. On the first energy level, that one fills up. There's the 1S. And the second energy level, now remember, I'm drawing these like rings, but we know from our other discussion that these sublevels don't look like rings. We're just drawn this way to make it a little simpler to understand. But we can think of this second energy level as being divided into two sublevels, the 2S, the 2P. The third energy level into three sublevels, the 3S, the 3P, and the 3D. Now this is where we end up with a little bit of a situation, because when we get out to this size energy level, we start getting the energy levels so big that they start blending or overlapping. So what happens is that right in here, when we start the fourth energy level, it actually ends up being at a lower energy state than that last sublevel in the third energy level. So we've got these rings and this that we're representing them with, and this 4S again is just kind of oozing over an energy in front of that 3D sublevel, and it's overlapping. And as this atom gets bigger and bigger and bigger, it gets more and more and more and more complex and more overlapped. So how in the world are we supposed to know what the order of those sublevels is going to be? Again, the process is called overlapping, and we need a periodic table in order to determine what that's going to do, what that order is going to be. So what I would like you to do is to pause this picture, take out a blank periodic table, and use map pencils to color in these sections. We have different sections here. This section here is called the S block, numbered 1 through 7S. This section over here is called the P block, numbered 2 through 7P. Notice this rogue helium here. Make sure when you color it that you color it the same as the first two columns. It is actually an S element. This middle section here is called the D block, and finally this bottom section down here has our F block elements. And what that means is that the last electrons in those atoms are in that particular kind of sublevel. For instance, if we're looking at sulfur here, the last electron in sulfur would be in a P sublevel, specifically the 3P sublevel. So make sure when you're coloring these that you also write in these different sublevel names in the correct position so that you can refer to this later. So once you've got this colored and labeled. If you'll look back at our example, you'll see that the first example we want to draw is nitrogen. The first thing we're going to do with nitrogen is to figure out again the order of the sublevels, figure out exactly which sublevels are going to have electrons in them. Now, if we go back to our periodic table, we see nitrogen over here. And we see that nitrogen is a 2p element. And that means that nitrogen's last electrons are in that 2p sublevel. We know, according to the Aufbau Principle, that the atom is going to fill from the inside out, and so that means all of the sublevels that occur before the 2p are going to have electrons in them. So how do we read this chart? Well, what I'm going to do first, before we continue with nitrogen, is to simply write all of these sublevels in order. In order to do this, you're going to simply start reading from the top, left to right. Make sure when you get to the bottom of the chart, you're just going to have to trust me on this, that right here we are going to draw little arrows down from the 6s down to the 4f here, and from the 7s down to the 5f. Because when we get to there, we're going to notice that these bottom two rows actually fit up into the main body of the periodic table. They simply move this section down so the whole thing fit onto a single page without taking up and being too small, too skinny to read. So reading from left to right, we see that the first thing we come to is a 1s. And so I'm going to write this across the top in just a running order. 1s. The next thing we come to is the 2s. And going across, we see the next thing that we come to is a 2p, then 3s, 3p. The next row starts with 4s, and this is our first instance of overlapping. 3d comes next. After 3d, we have 4p. After 4p, we have 5s. 4d, 5p, 6s. Notice what happens after 6s. I drew that green line with an arrow down to the 4f. So it's going to pick up the 4f. And after the 4f, we're now going to pop back up and pick up the 5d. After 5d, we come to 6p. After 6p, 7s. Notice what happens after 7s. We pick up that green arrow and move down to the 5f. After the 5f, we pop back up and pick up 6d. And finally, although it doesn't show them on this chart, there are elements that have been discovered that are bigger than the ones shown in this chart, so we are going to write down 7p. Back on the AP test a couple of years ago, it asked about a hypothetical 8s element down here, so that was a really interesting question. So this is the running order of the, up here is the running order of the sublevels, including all of the overlapping. We're going to have to be able to represent this and recall this for the test, so make sure you've got this periodic table labeled correctly. So now that we've got this order, let's go back to nitrogen. We see again that nitrogen is a 2p. Notice also that nitrogen is the third element in its block. That's going to be important to us in just a second. So notice that that's the third element in its block. So moving back to our notes, We're going to write the sublevels that nitrogen has, 1s, 2s, and 2p. Above those sublevels, we're going to write blanks representing how many orbitals they have. A blank is going to represent for us an orbital. Remember, those orbitals can hold 2 electrons and they have to be spinning in opposite directions. We're going to represent those with arrows, and since the arrows, we have to write a lot of arrows on a couple of these structures, we're going to write these arrows with, as kind of a half arrow up and a half arrow down to represent that these are electrons spinning in opposite directions. So these are our electrons. So for our orbitals, if you look and remember from the last discussion, we have one orbital in an S type of sublevel, one orbital, no matter what kind of S sublevel it is, we're going to still have one orbital. P sublevels have 3 orbitals, and so this is how we're going to draw that representation for nitrogen. Now remember, the lower sublevels have to be full. And we just showed how we're going to represent that with those up and down arrows. So we're going to put an up and down arrow in the first sublevel, an up and down arrow in the second sublevel. And for the third sublevel, we're going to look at something called Hund's rule. Now, we skipped Pauli exclusion principle. I apologize. The Pauli exclusion principle simply says no 2 electrons can be in the same atom with the same 4 quantum numbers, the same address. In other words, you can't occupy the same space at the same time. The only way we can have those electrons exist in an orbital at the same time is if they have opposite spins. This is why we have the up and down arrows represented in those orbitals. Hund's rule, I kind of think of it as I want to sleep in my own bed rule, or I want to sleep in my own orbital rule for the electrons. They are, remember, they don't like each other. They tolerate each other when they're spinning in opposite directions. But since nitrogen was the 3rd element over in the P block, let's go back and just recall that real quick. The 3rd element over in the P block. What that indicates is that nitrogen has 3 electrons in that 3rd block. Boron would have 1, carbon would have 2, nitrogen 3, oxygen 4, fluorine 5, and neon would have 6 electrons in that 2p sublevel. So since nitrogen has those 3 electrons that we need to represent, and they all want to sleep in their own orbital, we're going to show each of them in separate orbitals, all with the same spin, and that will be the orbital notation for nitrogen. If, for instance, it were carbon, we would simply not have the arrow in the last blank because carbon only has 2 electrons in the 2p sublevel. Just because there's an orbital there doesn't mean there's necessarily an electron in it. I'm going to draw these in green because I don't want you to write this down, but if this were oxygen, for instance, oxygen has 4 electrons. That 4th electron would have to come in and come down and double up in that first orbital. If it were fluorine with 5 electrons, then we would have another electron in that second orbital. And finally, neon, as we said before, would fill up that last orbital. Again, for nitrogen, however, we want just those red electrons, those red arrows representing the electrons. So let's look now at iron. We go back to our periodic table. Iron, right here, is a 3D element. What that means is that iron's last electrons are in the 3D sublevel. And notice that it is 1, 2, 3, 4, 5, 6 spaces over in that D sublevel, which means that 6 of its electrons, its last 6 electrons, are in that 3D sublevel. We are going to write down all of the sublevels up to and including the 3D for our orbital notation. So as we go back here, and you can follow along with your periodic chart, we are going to need a 1s, a 2s, a 2p, a 3s, a 3p, a 4s, and a 3d. Remember that now we put orbital blanks over the top for all of the s's, no matter what the number is in front. They all have 1 orbital in them. The p's, no matter what the number is in front, have 3. And d's have, as hopefully you remember, 5. We are going to fill up all of the lower sublevels, just like the Aufbau Principle told us to. And we're going to fill up all of the sublevels up until the last one. Recall that Hund's rule says that all those electrons want to sleep in their own bed, and we've already established that iron is the 6th element over in its block. So we need to put 6 electrons in these orbitals. So we are going to put those electrons in 1 orbital at a time. And we've shown where the first 5 electrons are going to go. Recall that now we need a 6th electron, and it's going to need to start doubling up again in the first orbital. So that's the the orbital notation for iron. Our final one is the most complex. It's the longest one. I'll be drawing a lot of arrows for this one. Platinum. So as we look at platinum on the periodic table, platinum is way down here, number 78. Platinum is a 5D electron, a 5D atom, which means its last electrons are in that 5D sublevel. And notice it's 1, 2, 3, 4, 5, 6, 7. It's the 8th element over in that D block. So that means we've got to find 8, or put those 8 electrons into that last sublevel for platinum in the 5D sublevel. And recall that all the other sublevels must be written down in order and filled before we get to that 5D sublevel. So you can follow along as I go back to the notes and see how this order goes again. Please use the periodic table. Don't make the mistake of using the running list up at the top of the periodic table, because if you use that all the time, you won't be able to remember how to do this with a periodic table on the test. So let's go back to our notes, and we'll start writing down these sublevels. Leave plenty of space for the D's and F in particular. We have 1s, 2s, 2p, and I will have to go to a second line for this one. It's pretty long, and I don't want to squish it too far together. 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and this is where people make their mistake. After 6s, remember, comes 4f, and after 4f, we get our 5d. Now go in again and put the orbitals above. All of the s's get 1, so put orbitals, 1 orbital for all of the s sublevels. All of the p's get 3. The D's, remember, get 5. And that F, for the first time we do an F, and it gets 7. all of those orbitals get filled up until we get to the 5D. So now we start writing a bunch of electrons. You might practice when you get to a sublevel that has more than one orbital of making sure you put those in one at a time and then going back and doubling up. That'll prevent you from making mistakes at the end. So fill all of those up. And I think you can see the reasoning for drawing half arrows now. Finally, we get to the 5D. Remember, there are 8 electrons in that 5D. The first 5 are going to go in individual orbitals, and then we'll go back and start doubling up. So we've done 5, 6, 7, and 8, and that is the orbital notation for platinum. In our next lesson, we'll look at how to assign quantum numbers to these elements.